All right, now that we have a better understanding of continuity and how to find limits, let's talk about piecewise functions. So essentially, piecewise functions are functions that are made up of several functions. So if you combine parts of several functions to make a single function. Okay, so for example, let's say we have something like f of x is equal to 1/2 x plus 1 when x is less than 4, and negative x plus 6 when x is greater than or equal to 4. So essentially this means on our domain, whenever our x values are less than 4, this is the graph of the function, or the equation for the function. When x is equal to or is greater than 4, then this is the equation for the function. So now if you graph this, so our interval is from x is less than 4, okay? So at x less than 4, it's this line, x, and it goes over 2, down 1, over 2, down 1. So it looks like a straight line. Okay, so as you can see, I made an open hole right here because for this equation, 1/2 x plus 1, the value x equals 4 is not included, so it's an open circle. Then at 4, we're using this equation right here. Oh, oops, I completely drew this graph wrong. Let's fix that real quick. Okay, sorry about that. Our graph should be a positive. Our slope is positive, so it should be increasing. So here we are at 1, 1, 2, 3, 4. So we go over 1, over 2, up 1, over 2, up 1. Okay. Okay, sorry about that. So, like I said, from negative infinity to 4, we have this line, but at 4 is not actually included in the domain of this function, so it's an open circle. So here's 1/2 x plus 1. Then at 4, we have to use this equation, negative x plus 6. So at 4, its value is actually at 2. So then we start here, and then we're decreasing. So over 1, down 1, over 1, down 1, and our function looks like this. So the two pieces of our single function combined make this graph. Okay? And that's a piecewise function. Now, piecewise functions are obviously very much connected to this idea of continuity, because to be continuous, as we've covered already, we have to meet the 3 conditions of continuity. So for piecewise functions, this is something that has an extra layer of something you have to check, because we have several functions within one function. Okay? So let's talk about domain and range to kind of help us understand how to graph piecewise functions as well. Okay, so domain and range. So as I hope you remember, the domain of a function consists of all possible input. Okay, so what does that mean? For a function f of x, the domain is the set of all x's. Okay, so whatever x you can put into your domain such that f of x is not undefined or imaginary. So don't worry about that imaginary part. We'll talk about that at some point in the future, but we want to focus on this not undefined. So we want to find all possible x's that make our function defined. Okay, if it makes it undefined, it's not in the domain. Domain is written like this. There are two ways you can write it. You can either write it in interval notation. Essentially, you're telling me which interval the domain belongs to. So, for example, if it belongs to negative infinity to 1, and then from 2 to infinity, okay, they're telling me, oh, these are the intervals that that are the possible x's that can go into my function. This right here is a union symbol. It just means and. Okay, so my x's belong in this interval and this interval. Okay. The other way you can write domain notation is with set notation. Okay, essentially, essentially you could say that everything that can go into my domains are all the x's such that x is greater than or equal to negative infinity, or it can't really be equal to negative infinity, I guess. So let's fix this. Okay. And is less than 1. And it has to be between 2, anything greater than 2. So this is essentially saying all the x's, such that, and then these conditions, such that x is between negative infinity and 1, and 2 is greater than x. So because we go all the way up to infinity. Okay? So you can actually just shorten this to all x's less than 1, because that goes all the way to negative infinity. Okay? So two ways, interval notation, you're telling me which intervals I belong to, or set notation, you're telling me what set of x's, which x's apply to my domain. Okay? Range are all possible outputs of my function. So domain's all my possible inputs, range are all my possible outputs. Such that, again, we don't want f of x to be is not undefined or imaginary. Okay? So again, we don't want an undefined number or an imaginary number. You can also write range with interval notation and set notation. So interval notation for range, okay, is a big R. Let's say all my possible outputs are 3 to infinity. So that's the interval in which all my outputs belong to. And then set notation, similar to the set notation we saw earlier, is a big R. So my range is all the y's, right? So my range are my outputs, meaning they're the y values. So my range is all the y's such that y is greater than or equal to 3. Okay? I'm using this domain right here. So again, this is all y values such that y is greater than or equal to 3. So you can either write in interval notation or set notation for your domain and range. Now, all of the times this is important because you'll be asked to analyze the domain and range of different functions to see what restricts functions. Okay? And for piecewise functions, this is something that you can examine as well. So let's do an example. Let's say I tell you to first graph f of x equals x squared for x is less than or equal to 0, and 2x plus 1 for x is greater than 0. So if we graph this, okay, from negative infinity, so anything less than or equal to 0 is this parabola. Looks like this. Okay? And then for anything greater than 0 starts here and is a line that goes over 1 up 2, 1 up 2, okay? And it's a straight line, okay? So this is my x squared from negative infinity to 0. Here's my graph 2x plus 1 for anything greater than 0. Now, if we look at the domain of this, so all our possible inputs are all numbers. We can put in any number and we would get a value. It wouldn't make it undefined or imaginary. So our domain is either from negative infinity to infinity. You can write it in interval notation. Or our domain is all the x's such that x is between negative infinity and positive infinity. Okay, this is the set notation. Our ranges, okay, as you can see, we have values from positive infinity all the way to 0, and then from 1 to positive infinity. So, sorry, negative. Yeah, so we don't have any negative values. Okay, you guys can see that. And we don't have any values between 0 and 1. See, there's nothing here. So then our range is equal to, okay, 0 to positive 0. Oh, we actually do have values. I'm sorry, I apologize. That's a mistake. We do have values from 0 to 1. They're right here. You see them? I'm sorry about that. So our values are actually everything from 0. We have a value at 0 to positive infinity. And then if we write it in set notation, it's all the y values such that y is greater than or equal to 0. Okay? So either way, we can describe our domain and range as we examine this piecewise function. So now you do an example. Okay? You graph f of x is equal to x plus 2 squared for x less than or equal to negative 2, and 2 times x plus 2 plus 1 for x greater than negative 2. And then go ahead and find domain and range and figure out where f of x is discontinuous. So as you can see in the above example, we have a discontinuity at x equals 0 because the limit from the left-hand side does not equal the limit from the right-hand side, which automatically means, we don't meet the first condition, we're not continuous. So at x equals 0, we are discontinuous, okay? So you try